Welcome, everyone. We're very excited to bring you today's webinar presenting our latest addition to the ever-expanding BigML platform in the form of image processing. My name is Atakan Çetinsoy, VP of Predictive Applications for BigML, and I will be moderating today's webinar. And the presentation and the demo will be given by my colleague, Charles Parker, BigML's VP of Machine Learning Algorithms. Image processing is a very versatile technique being used in many industries, such as manufacturing for quality control, healthcare for medical diagnosis, and retail for visual search, among other operational contexts. For BigML, this is a much-awaited milestone release that takes our platform to the next level by allowing any user, regardless of their prior background in machine learning, to generate insights from their image data in a self-serve manner. Enabling this level of all-in-one image processing accessibility is no small feat. As a matter of fact, the 2021 Kaggle State of the Machine Learning Survey, conducted among 25,000 plus machine learning practitioners, has found that even among the more experienced, the adoption rate of more sophisticated techniques such as various flavors of deep learning still run only in the 25 to 40% range due to their inherent complexities. After pioneering the entire machine learning as a service category a decade ago, and later introducing advances like one-click modeling, end-to-end server-side machine learning workflow automation, and infrastructure-agnostic auto deployment and auto scaling, BigML is now helping business analysts, developers, scientists leap ahead with all-in-one super streamlined image processing. We have architected BigML image processing from the ground up in a way that seamlessly treats image data as just another data type. To be more specific, as you will witness shortly, BigML users can now utilize the no-code BigML dashboard interface to mix multiple data types together for better models and predictions, while enjoying the built-in traceability and explainability features of the platform. Moreover, as is the case for other data types, image processing models can also be managed through the comprehensive BigML API by developers. With a number of popular pre-trained convolutional neural nets, BigML users can iterate rapidly and zero in on production quality image-based models in hours or days instead of many months with other tools. This improved experience is in sharp contrast to having to constantly master new open source libraries, installing and updating third-party plugins, and manually downloading large pre-trained models on your own. It gets even better because no GPU or specialized hardware is necessary to enjoy all of the above. In conclusion, BigML image processing is the only no-code commercial implementation of its kind that melds not only deep learning, but also other supervised and unsupervised learning techniques underpinned by composite sources, blending image and non-image data together, while allowing users to tackle image labeling as they need. Before I turn it over to Charles here for more, a few quick reminders. First, we have reserved time for live Q&A at the end of the presentation, so be sure to stick around for that. During the session, you will all be muted. At the end of the session, I will unmute you if you raise your virtual hand to ask your question. You can also ask questions in the questions area on your GoToWebinar client during the session, and we will share the answers as we go. Finally, if you have general questions or suggestions, feel free to email us anytime at info@bigml.com. With that, I'd like to pass the baton to Charles so we can see BigML image processing in action.
All right, thanks very much, Atakan. As Atakan said, my name is Charles Parker. I'm the VP of Algorithms here at BigML, and we're here to introduce image processing on the platform. A little summary of what we're going to do here. First, we're going to talk about applications. So image processing is no good if you don't know what to do with it. So we're going to talk about a whole bunch of applications. Some we've solved with the platform, others we haven't tackled yet, but this is just to kind of get your imagination going, thinking about what you could do with image processing if you could integrate that into your own tech stack, into your own applications. Then we'll do a simple image classifier with BigML, show you how easy that is to get an image classifier up and running. And then we'll step out a little, zoom out a little bit, talk about image data management on the platform. How do we compose collections of images? How do we upload collections of images? How do we combine those images with other relevant data to create classifiers based on all that data? And then finally, we'll kind of dig deep into the platform to see what some of the features are we can use to solve these non-trivial image problems. So it's pretty easy at this point to solve an image problem where you've just got an image and you want to assign a label to it. You know, there are the algorithms that we have, the software that we have is very good at that simple problem. But what happens when the wheels start to come off those assumptions? When you don't just want to apply an image label to an image, if you have different data, if you want to go faster, if you have a different sort of problem, can we solve those things? And the answer to a lot of those questions on BigML is yes, you can in fact solve those things. And we'll talk a little bit about examples like that. Starting from the top, a few applications of computer vision. At this point, there are a lot of really well-known applications of computer vision, a lot of places where these models work really well and help people and make people money every day in the real world. Just to go through a few of them, there's ecological models that you can use to do land use classification. You have satellite images. You want to be able to tell what part of that satellite image is a forest and what part is a river, what part is a field, etc. Doing things like ecosystem health management, where you've got camera traps set up to identify animals. You want to know what's walking through the forest. You want to get an estimate of those animal populations. You can do that a lot easier if the cameras are able to automatically classify what animal that they're looking at. Transportation, BigML has solved a couple of use cases in this area, as I'll go through in a few slides, but things like tollway monitoring, you want to look at the tollway, you want to make sure everything's running smoothly. If there's some kind of accident on the tollway, you want to maybe shut it down, route people around it. So if you're in charge of those roads, you can ensure as smooth of an experience as possible for people. Automated billing, you have people going through gantries that have cameras. You want to capture their license plate and automatically bill them without having to, deal with things like transponders. Medical imaging, you want to, this is also kind of becoming more and more well-known, all these radiological images, CAT scans, X-rays, PET scans, MRIs, you'd like to be able to look at those things and at least give a first approximation of what a radiologist might say about those things. Segmentation, for disease identification, so getting, drilling down a little bit. If you have a particular area of the image, say you're looking at cancer, you want to identify exactly which pixels in that image are visualizations of that cancer. And then finance, again, a whole bunch of applications in finance that we already see every day. One interesting one is form classification. You have a bunch of forms coming in, like tax forms. You want to automatically tell which form you're looking at and route it to the proper person or the proper agency to deal with that form. Insurance claim estimation is another interesting one that we're going to talk more about as the webinar goes on. You have say you get in a car accident or you have a house fire, you can take a picture of that and maybe guess how much the claim is going to be. So the classifier can tell whether there's kind of severe damage or moderate damage to the house, and it can make again, a first order approximation of how much that insurance claim is going to be. And there's other examples, of course, that I haven't listed here too. Manufacturing is another one we're going to talk about. What if you could take an image of parts as they come off the assembly line and see if they're defective, right? Rather than having a human there needing to inspect each part, you just have an imager there, and the parts go through the imager and tell you whether or not that part looks good. So lots of applications here. Kind of your imagination is the only barrier to figuring out something interesting to do with this particular type of machine learning. Anytime you have the opportunity, you've got an imager, you've got a camera somewhere, you've got an infrared imager, anything that can take a 2D pixel representation of a scene or a thing, and anytime you want to find out what's in that image, find out what that image means, that's where you can do image processing. So basically anywhere you can stick a camera and you want information about what that camera is looking at, that's what image processing is for. So there's a lot of cases where it can be used. So just digging a little bit deeper, here's an application we solved for Global Via. They're doing tollway monitoring. And a lot of what they want to do right now is just track the people coming onto the tollway and leaving the tollway. First of all, we get front and back images of the car as it goes onto the tollway. We take a look at the license plate. We need object detection algorithm to tell us what the characters are on the license plate. So we do plate detection first. We classify the plate as to what state it comes from, and then the state itself. There's different patterns of letters and numbers that happen on license plates from different states. So once you see the characters on the plate, once you see the letters and numbers that compose the license number of the car, you can make a better guess as to what state that came from, even if the markings specific to the state are somewhat obscured. And so this is a nice example because you've got all of these models. You need all of these models to make the system. And then you yourself, the person with the domain knowledge, the developer with the domain knowledge, can combine these models into a coherent system by using kind of bespoke business rules. So for example, in this particular application, you have images of the front and back of the car. You have images of 2 different license plates. You need, if we read both of those license plates and we get a slightly different set of numbers and letters, we need some way of combining those 2 predictions of what the license number of the car is into what we think the license number of the car is. So that, you know, happens more in business rules, more with kind of programmed logic knowledge, if you want, that you're adding to the classifier by hand, rather than more machine learning. So if you've got 2 different patterns of digits, we know as humans, oh, there's usually, you know, 6 or 7 numbers. If we only see 5, then we better trust. We're more likely to trust the prediction that has 6 or 7 numbers. So things like that, human knowledge combined with these machine learning models is what ends up making a successful system. And so what we're trying to enable at BigML is for you to easily train those models so you can focus on the part that you're very good at already, which is knowing about the domain that you're in, knowing what rules to apply to those images to create something useful. Marksmanship training is another application that we're working on for a subsidiary of BigML. And here, again, the basic idea is to look at somebody who's shooting a firearm and tell where exactly, tell how they're shooting. You know, we have pose estimation data from various models. We want to know what they're doing. Are they shooting? Are they holstering the gun? Are they taking the gun out of the holster? We have a camera pointing down range. We want to look at that target. We want to know what sort of target we're looking at. We want to know when an impact, when a hole appears in the target. We want to know where that hole is precisely and when it happened. We have a zoom on the person's hands holding the firearm. We want to know what type of firearm it is. We want to know if they're holding it correctly. So again, a lot of different models here, and it takes not just these models, it takes a lot of models trained, and then it takes logic programmed by the user to pull all those models together into a coherent system or a coherent application. All right, so this was all just to set up kind of what BigML is trying to do. What is BigML trying to do? We're trying to give you the tools that you need to create these models so that you yourself can create a successful application around them. And so how easy is it to create a model in BigML? And we've tried to make it incredibly easy. And in fact, as we'll talk a little bit more about, we've completely eliminated a lot of the background knowledge that you need to create these models from scratch. So here's an example of a simple example where you're looking at small images of a handwritten digit and you want to classify those images. This example is trotted out all over the internet. It's a really famous data set in the machine learning world. It's a fine example. Humans and computers at this point do about the same. At this example, we have the same level of accuracy pretty much. So it's easy for computers to do. It's easy for humans to do because most of the vast majority of us know how to read digits. But now let's take a look at a slightly different example. Here's a collection of x-rays of chest x-rays of children. They're pediatric chest x-rays. And some of these children in this slide have pneumonia and some of them don't. Now I, having no special training or expertise on looking at x-rays of children, have no idea which are which. I don't know. And I have talked to various friends and family members, the friends and family that I have that are not physicians, and they don't know this either. There's no, I'm telling you ahead of time that some of these children in these images have pneumonia and some of them do not, and I'm not really sure which are which, and nobody has explained it to me. But looking at these images, there's no obvious difference. You know, contrast that with this, where the difference between a 0 and a 4 is apparent to anybody, even those who don't know what a 0 and a 4 is. These images are not like that. If you are a radiologist, or maybe you have better vision than me, you will know that the children on the left do not have pneumonia and the children on the right do in fact have pneumonia. So that's a pretty difficult thing to see, at least for me, at least for a human. But it turns out that a computer can do it without too many problems. And so what does this look like to do this in BigML? Well, we have a zip file with those images. We create a data set from that zip file on the BigML platform. If we want to do a nice evaluation, we can split this data set into a training data set and a test data set, the usual way we do with any machine learning data set. We'll train a model on the training data set, and then we'll evaluate it on the test data set. Sort of the simple, usual set of things that we do with any other machine learning data set. And that's something that's going to come up over and over in this webinar, is that images are not super unusual. They're just another input to machine learning algorithms as far as we're concerned. And so let's take a look at what this looks like in the BigML platform. Basically, I have a zip file which has all of those images in it. I uploaded that zip file, and I did this ahead of time because it's a 1 GB data set, as you can see. You can see that we've gone through the zip file. Here's the paths of all the images in the zip file, and we've also automatically extracted the label using the directory, the subdirectory that the image was in. So all these images in the zip file were in a subdirectory called normal, and so we've extracted that label for these. And if we go through our data set, again, here's the data set. I've already split it into a training and test data set. If I look at the training data set, we'll see again that this looks like any other BigML data set. We have the image. That's one of the features in the data set, one of the fields in the data set. We have the file name of the image. We don't use that by default. We don't consider it meaningful. And then we have the label that we extracted from the directory. So as you can see, about 3/4 of these images in this training data set, the children have pneumonia, and about 1/4 they don't. I've already trained a deep net. We could just, this is how I train this deep net ahead of time. You just go to one-click deep net, and we do the rest. And we'll talk about what the rest is as we go on. But if you look over here, you can see I've already trained one deep net from this data set. So let's take a quick look at it. By default, we're going to do a convolutional neural network if you train a deep net on the platform on image data. And we're going to hold out some data from the data set to make sure we're not overfitting that training data. And what we show you when you're done training the model is we show you that the images from that holdout set and the predictions on those images. So because that those images were held out during training, that should give us a rather good estimate of how good the performance is going to be in the future. On that holdout set, we didn't see that during training, and so it's a pretty, it gives us a somewhat good guess of what performance is going to be. And as you can see, performance is very good here. We have a sample of the correctly predicted images, the vast majority of these images. We've made the correct prediction, both normal and pneumonia images. And down here we see one incorrectly predicted image, where the probability was very close to 50-50. So that's a really good outcome for training this data set. But of course, it's not a substitute for an actual totally unseen holdout set. This validation set gives us a good idea of what the performance was, but it's different from a completely unseen holdout set. And so you can do an evaluation on that test data, which I already have. And if we look at this evaluation, we can see that it mostly bears out the numbers from our holdout set. We've got 97% accuracy, a bit lower. You would kind of expect that, but overall, this computer vision model is doing extraordinarily well on this problem that is difficult for humans to solve with no special training. Now, and finally, if we want to, we can go to predict here, and now that we've trained this model, we already have an API endpoint where it's live, right? The model is working right now, and you can use it to make predictions. We can drag an image here. We can select an image that we've already uploaded to the platform. If I go here, there's my chest X-ray images. So this model is already live. Anybody can make predictions with it. Well, anybody who has access to it, anybody who has your BigML API key can make predictions with it. and nothing more has to be done. To operationalize this model, to have this model sitting on a server running, making predictions, is already finished. So that's kind of a nice outcome, right? We've got this model, we've got a problem computer vision can solve, we've got this model that we learned that an evaluation says is very good at its job, and we've got it live running on a machine in production, essentially. Now, I don't want to, of course, this is like the usual caveat with this medical imaging stuff. This is not, of course, a replacement for a trained radiologist. This computer is very good at labeling these images, but it's, first of all, it's subject to the data that it was trained on, which might or might not be labeled accurately. And second of all, it's of course not a substitute for a clinical evaluation of a person with an X-ray that looks like that. But if we're talking about cases where we've got a rural area where medical care is difficult to find, or we've got an area of the world, a poor area of the world where radiologists may be in very short supply, in those cases, some of these models may be able to bring some of that expertise to a place where it can be useful, rather than the alternative, which would be to wait or to not be served medically at all. So with that caveat, kind of the important thing for me here is that looking at these images, I can't tell which images have pneumonia and don't, but yet the computer can do this with extraordinary accuracy. And this is the part of kind of image processing, the latest iteration of computer vision that's very, very exciting. We can solve problems like this that are hard, even for humans, without too much effort. And BigML, of course, is driving that effort even further down. So that's good. But there's so much more than that. And that's what we want to talk about mostly today, is what can we do that's not just applying a label to an image. So saying this image is normal, this image has pneumonia, that's something that's easy for current software to do. BigML makes it easier, and we'll talk about all of the things you avoid in a second. But what else can we do? First of all, if you have a problem other than just putting labels on an image, we can solve that problem too. We can do regression, we can do unsupervised learning, and we do this by extracting meaningful features from the data at sort of a different level than CNN does, than a convolutional neural network does. And we can also combine those features with other features in order to do predictions from 2 images at a time, or from an image plus text, or from an image plus a bunch of numbers. We can handle all of those cases. So again, the usual thing, mapping an image to a class. Yes, BigML makes that very easy, but also if you dig into the platform, you can solve a lot of other problems with it that involve images. And so we're gonna go forward and talk about what that looks like. So first of all, deep learning. If you just want to do deep learning, we just did it. If you just want a CNN that applies a label to an image, then we're done. I just showed you exactly how to do all that, and you don't really have to do anything else. In the background, what we're doing is we're trying a bunch of different CNN architectures, the ResNet architectures, some very simple architecture. We're trying pre-trained features. We're trying fine-tuning those features. There's a lot of different potential models that you can get when you just go upload a zip file full of images and say, give me a deep net to predict that label. There's a lot of different images you can get, and we try to size the network basically to the amount of training data and the complexity of the problem that you have. So if you've got an easy problem, you'll probably get a simple network that will run very quick. If you've got a harder problem, we're probably using a pre-trained network. We may have done some fine tuning on it, and you'll get the benefit of a network that's been trained on millions of images in the background. So that's great. That's a lot of what deep learning can do right now. That transfer learning, a bunch of different architectures, scaling the architectures to the size of the inputs and the complexity of the problem. These are all nice things about deep learning. And so very often when you've got one of these image problems, you just want to apply a label to an image, deep learning is the best thing that you can turn to. But a lot of times it isn't. And so let's talk now about what we offer just outside of that deep learning bubble. First of all, one of the most important things you need to be able to do when you've got an image problem is just manage your data set. And we allow you to manage your data set with user labeling tools and something called composite sources, where we're going to treat each image as its own little data source, and we're going to allow you to compose data sets out of different combinations of those sources as you want to. We have a variety of image feature extraction techniques. So if you don't want to just use deep learning, we have a variety of ways of saying, hey, instead of using deep learning, here's some more traditional computer vision features. Use those to feed one of the standard BigML algorithms. Finally, we do have convolutional neural networks for classification and regression problems. You can solve regression problems just as easily as you can solve classification problems with single image input. And then handling of infrastructure concerns. And you see the images that we've chosen for the right side of the slide are all about those infrastructure concerns. And this is something that's not trivial and it's not cheap. I pulled down some images of recent prices for graphics cards during the chip shortage, and they're running $1,000, $2,000, $3,000 for a state-of-the-art graphics card. Imagine if you're trying to, you want to train 10 models, you want to do that fairly often. Even if they're small models, you'd like a GPU for each model that you're training in parallel. And so this gets real expensive real fast, right? You also need the server space, and all of a sudden you've got an IT guy who needs to manage all of this networking stuff. You've got to train your developers to access that cluster and run models on that cluster. So as soon as you're doing pretty much anything other than, spinning up a Docker container on your own desktop to train these things, as soon as you're doing anything other than that, you're running into a lot of dollar signs. And with BigML, that's one of the main advantages for me personally, at least. I train these things. Like I said, we've been working with a lot of third-party vendors, making applications for them. When I train these things, I'm turning to BigML more often than not because I don't want to tie up my machine with one of these massive training runs. I just go to BigML, they spin up a GPU machine for me, the model trains, it's done. It comes back as white box JSON that I can just download. And we're all set. That's not something you can do unless you've already done all of the development that we've done to make this possible, gotten all of the drivers and all of the versions of all of the software in all of the right places, having a nice auto-scaling system that can scale the infrastructure up and down as needed for all of our customers, whether they're in a private cloud or whether they're using the public deploy. This is stuff that's already done for you if you're using BigML. And for those people who are thinking of rolling their own image processing capabilities, their own deep learning capabilities, there's a lot to think about, and there's a lot of money to be spent along those lines. All right, so zooming back in a little bit. As I said before, you can upload a zip file to the platform with a bunch of images in it, and you get a nice image data set. But what if we need to compose an image data set and kind of add to it incrementally? And for this, BigML's solution is image labeling and composite sources. So a composite source is a source that contains a bunch of subsources, or component sources, we call them, and those are the individual images that you've uploaded. And while this composite source is open, you can add images or add labels to images, and that allows us to preserve immutability. As soon as you say, okay, I'm done editing this source, or I want to train a model from this composite source, I want to train a deep learning model, you close the source, it can never be edited again. And this way, you can always go back to the source from which the model was trained. Because you close the composite source before you train, that means later, after you've trained, you can say, hey, what was the data this model was trained on? Oh, look, it's right back here. I know it's right back here because you're not allowed to change the data that the model was trained on after you train the model on it, right? So this closing the source is kind of a crucial step that preserves the audit trail between the model and the data. And if you want to edit or add images to the source again, what we have you do is clone the source, The clone is kind of a shallow copy. It just points to all of the constituent images, and then you can add images to it as you see fit, or change the labels as you see fit, correct errors, and then when you're ready to retrain, you close the source and then you retrain again. So you always know for a given model, hey, that model was trained on this data and only this data and precisely this data. And we know that because we don't allow the data sources to change once they're closed. And so what does that look like? If we go back to my sources here, I have another file like this. So this is an example of what you might upload to the BigML platform. These are just two sets of images, a directory full of gorilla images and a directory full of horse images. And if I go down here, I have this zip file, which is exactly just this folder zipped up. And so I can drag it into there. This is a fairly small file, so it uploads pretty quickly. And it'll be queued for a moment while the servers spin up, because no one else is using this particular server right now for my demo purposes. But right here we have the same zip file that I've already uploaded. And so if I go into it, I see exactly what I saw with the X-ray data before. I have the path to each image in the zip file, and I have the label extracted from the directory, and it's extracted from the innermost directory there. So we do, we don't make the silly mistake of taking the outer directories for the label. And if I look here at the images, you'll see I can edit the label if I want to. I made this horse into a gorilla earlier. Oh, that's a mistake. Let's change the label to a horse and save the label. And then we'll close this. Now this is a horse again, as it should be. If I want to add an image to this data set, I can just drag one. One way is to just drag one on from my desktop here. And then that creates the source. I go to add new sources. And he's queued for a second. And there's my source image. I select it and I say add. And so it updates the source, and it gives me the new composite, or the updated composite source with my quarter horse image in it. And all of this is available by the API. So if you want to bulk upload images and put them into a source with the API, you can do that. As usual, our UI is built entirely on top of our public API. So you're able to do anything that I'm doing here in the UI. You're also able to do that in code. And so if I go back to my sources here, you can see that this one is the one I just uploaded has finished processing. If I want to build a data set out of either one of these things, I can just go to close the source. If I go to one-click data set, it will close automatically. But once you close the source, it's not modifiable anymore. And now we know that the source is closed. You can see that here. And so when we build a data set out of it, when we create models based on that data set, we know that this data will never change. This is forever closed. It's frozen. And so any models that we train on data sets built from this composite source will always know exactly which images were used to train that model, and exactly what the labels were that we used to label those images. And so that's very nice, right? We're able to kind of have these image collections. We're able to add to and modify these image collections for doing image training, but also we're able to freeze those in place and preserve immutability, so that in the future, if we want to know about the data that this model was trained on, we can just go back to the data and look at it. It's there, it's frozen in time, and it's observable in the UI. So that's good, but what if we had more information? So let's kind of expand horizontally here and think about what else we could put alongside this image that would make this image classifier work better. we're doing image classification in a forest, and so we have the image itself, and we have the geo coordinates where the photo was taken. So that's very important, right? Because we know some animals live somewhere, and some animals live in other places. And so if we knew where the photo was taken, we could make a better guess as to what the animal in this photo was. The other information comes from the geopositioning system, right? We have the approximate altitude. So some animals live at high altitudes, some animals live at lower altitudes. We can take that into account as well. So if you want to add this information kind of alongside the image with BigML, all you have to do is put a CSV in that zip file and edit that CSV. And the important thing here is, again, that we just treat the image as one or more of the features that go with each dataset instance that we're trying to classify. So I have another kind of demonstration dataset here. Well, yeah, we'll go back here. I have another image demonstration dataset here, this Bluebird dataset. And in this Bluebird dataset, I have a CSV file. I have two directories full of Eastern Bluebirds and Western Bluebirds. Obviously, if you take an image in the Western part of the country, you're more likely to see a Western Bluebird than an Eastern Bluebird. So we have a classification problem between these two Bluebirds where the GPS coordinates where the photo was taken is very relevant. And if I look at the CSV in this zip file, you can see that I've got the file name of the image in the zip file, and I've also got the GPS latitude and longitude where the image was captured. So there's the relevant information. I've got the GPS altitude, and then finally the label of that instance. So this is pretty much as easy as it gets, right? You've got a bunch of images. You want some information to go with those images to do machine learning on all of the information jointly. You want to use the image and these numbers as inputs to classify this image, to classify this kind of instance as a whole using the image and the GPS coordinates. All you have to do is put in a CSV file like you would with any machine learning data set, and you'll get a data set that takes that all into account. And that looks like this. So I uploaded this earlier. You've got the file name of the image. You've got all of the data that we added alongside, and then finally the label that we apply to these things as well. And when you make a data set out of this, you'll see again that it looks just like any BigML data set, with the exception that you've got an image as one of the features. So you've got the file name of the image, all of the information that we put alongside the image, the label that we assign to the image, and then the image itself. And here's just as we provide you with histograms of the numeric features showing their distribution, we also provide a sample of the images in the data set. You can refresh the sample. You can look at these images in the data set. This one's a drawing. We do fairly well with this data set as well, whether or not you use the geo information. We do much better with the geo information, but we also do fairly well with the images alone. So that's kind of a simple example of this, right? We just have these two geo coordinates that go alongside the image, or these three geo coordinates essentially that go alongside the image, and we can learn to classify around those jointly with the image rather than having to just use the images alone. But if you think about that CSV file and you think about how you could put anything in there, the possibilities start to stack up in your mind. So let's suppose you're an auto insurance company, right? You have a simple regression problem here, as I mentioned at the top of the session, where you want to take a picture of a car that has been in a crash. You take a picture of the damage, you upload it to the insurance company, and the insurance company takes that image and they assign a dollar amount. They say this is probably about how much that's going to cost to fix. So this is a very simple regression problem, right? Regression model, you're just mapping the image of the car to a dollar amount. But now you see that CSV there and you say, what else could we do? Well, there's no reason we can't have two different images of the car, right? We would just add another column to the CSV with the other car image. So now we have 2 images that we can assign to a dollar amount. What about if you have telemetry data from the car? What if you have the state of the brake pedal or the angle of the steering wheel? Is that going to impact how much you think the accident is going to cost to repair? Let's go a step further. What if you have the police report? What if you know the text of the police report? Is that going to impact your estimate of the damage? What if you have phone data? A lot of, Allstate or various other insurance agencies have a phone app that you can use, like a safe driving phone app that gives you discounts in your insurance. What if you know all of that data? What if you know the accelerometer readings from the phone at the very moment the accident happened? What if you know if the screen was on or off? What if you know whether or not the driver was potentially not paying attention? Does that impact your estimate of the damage? So you can see here that you can do multiple images, you can do multimodal classification. All of this image can kind of feed into your estimate of the class here, of the label of the image, of the dollar amount. And all you have to do is add information to that CSV file. So I don't know if you've looked around, for those of you who are developers, if you've looked around for software that does this automatically, it just doesn't really exist. So if you're doing this, you're writing Keras code, you're writing PyTorch code, you're accessing different sorts of data structures. You're doing a lot of, you might be trying to do image augmentation on your own, you're composing layers of things, and then you're waiting forever for it to run on your local machine. This is the sort of thing that's made dead easy with BigML, using that simple technique of including a CSV file with your images to tell you how to put all that data together. So stepping to the side a bit, what if you don't have a simple classification problem? What if you don't have just a label you want to apply to the image? Like what if you have anomaly detection or clustering, a couple of the problem settings that we solve on BigML already with different sorts of data. Basically, all we have to do is transform each image that we have into a vector of numbers. And then once we've transformed each image into a vector of numbers, we can do any sort of machine learning algorithm on them that we can do with any set of numbers. And so deep nets have this kind of built in explicitly. The convolutional layers stack up, and then at the end, there's usually some kind of what we call a pooling layer that reduces the image to a vector of numbers. And then we do classification on the numbers that come out of that top layer. So basically, we can do that with the first several layers of a convolutional neural network, or there's a lot of, by now ancient techniques in the vision community that still work pretty well for a lot of these things that we can pull out as well. By default, BigML chooses something fast to do this, but we offer you a lot of choices. So you can, if you want, you can use a CNN to extract features like that. But the important part here is that if you're not using a deep net, you have to specify some sort of features to use for that algorithm, some way of reducing that image to a vector of numbers. And we give you a lot of choices. We choose one automatically, but we'll show you in a second how to change that. And so if I go back here to my sources, I have this casting example that I was just showing in that slide. Some of these images here in this example are in this good directory, and these are pump impellers, and most of them don't have any casting defects. I believe the ones that are bad are at the end here. So here's ones that have defects, and some of them the defects are even pretty subtle. So if we look at this one, like we've just got this scratch here, and that's a problem. But this is this data set, and we'd like to do anomaly detection on it because we only have a few bad examples, and we also don't know what bad examples are going to look like in the future. You can see these are really nasty. These defects here are more subtle, and so we don't know what's gonna come out of this thing in the future that might be wrong. And so this is what anomaly detection is for. You say to yourself, oh, if it doesn't look like most of the images that I have in this data set, then we want to flag it. And so I've already created an anomaly detector out of this data, and I wouldn't be showing it to you if it didn't do its job very well. And we'll see that, of the top 7 anomalies, 6 of them are genuine problems with the pump impeller. So here's the top anomaly, and as you can see, the image for the top anomaly is this nasty thing. And here, just for reference, we show you some of the good images. the same as we do with these histograms here. We show you the your value in orange, and then we show you the rest of the values down there. And so here, yeah, here's another nasty one. And if you page down through these, you see that we get the vast majority of the defects, even the ones that are a bit more subtle. If I click on one of these, you see this one, it's got some scratches there, but that's a little more subtle. What about this one? Let's take a look here. And so, yeah, even the ones that have just little nicks around the inner circle there, those are also picked up by the anomaly detector. And so when we do that anomaly detector, as I say, this isn't like deep learning where you have this sort of automated feature extraction that happens as part of the network. You have to specify what features you want extracted. And like I said, we make a default choice at BigML, so you don't have to think about it if you don't want to. But if you do want to think about it, we go here. If we go into the source, the original source, and I say, hey, I want to configure this source. I want to tell you specifically what features we should extract for non-deep learning, using non-deep learning algorithms. I go here, oh, it says I can't do that because I've frozen this in place, right? I've already created a model from it, so it's frozen. So I have to go to clone here, create a copy that I can work with. And again, this is a shallow copy, so we're not talking about duplicating all the data. We're just talking about creating a new shell that we can add to or modify with the same images in it. And here in this case, I want to go to configure source. I want to say, hey, do something different with my images, and I have all these options for extracting features. I can use a pre-trained CNN. I can use a histogram of gradients. This is what's selected by default. I can do wavelet analysis. That's for if you want to preserve texture information. You don't have to do any of this. Like I said, BigML makes a choice for you that we think makes sense and is fast. But if you know something about your images, like you know that color is going to be the important thing in your anomaly detector. You want to flag images that are the wrong color distribution somehow. We have this level histogram thing that is a histogram of all of the RGB levels in the image. That, if you train an anomaly detector on that, it will flag the images that are a weird color for you. And if you do this, if you do a histogram of gradients, which preserves edge and shape information, then it will only flag things that are a funny shape. It will ignore colors for the most part. And so this is an opportunity, again, we've made it very simple, so you don't have to do this, but if you dig in and you have some domain knowledge here, you can specify a set of features that will give you a nicer result. And so this is something, again, that's missing from a lot of platforms, a lot of software packages. Is if you want to dig in, if you want to specify things that aren't chosen for you, you really have to start writing code, or you have to dig under the surface. Here, all of these options are available in the API, they're available in the UI, so you can kind of get as complicated as you want without writing code. So that's great for unsupervised learning. As I say, if you have if you have a problem that cannot be solved by a CNN, that's not just a vanilla classification problem or regression problem, you need to extract features from the image in order to use one of the more traditional machine learning algorithms. And so we give you an avenue to do that. But this is also useful, so that was anomaly detection, and this is also useful if you want to do a model cascade. And these are things that are used in the computer vision community a lot, because running a CNN on an image is an expensive undertaking computationally. So we're usually talking about, even if you have a GPU, we're usually talking about tens of milliseconds, hundreds of milliseconds to run a decent sized CNN on an image that comes in. And it depends, it depends on the sort of GPU you have. But sometimes you're way out at the edge, right? Maybe you're on a camera, or maybe you're on a phone and you need this thing to run fast. Is there something else you can do here? And one of the answers here is to train a supervised learning model, a simple one like logistic regression, using some of those extracted features that are cheap, like histogram of gradients. In this way, you get a model that runs incredibly fast. And if that model has near perfect recall, but it has kind of a high false positive rate, but is still able to filter out the vast majority of instances as they're being predicted, then you save a lot of effort, right? You put this model right on the front lines. Most of the images only see this model and get rejected, and the other ones that are potentially positive fall through to the more complicated CNN to do all the fancy processing. And this comes up a lot in image processing, because a lot of the times you're talking about problems with huge class imbalances. So security cameras come to mind, right, where the vast majority of images you see on a security camera are normal. And so if you can train a model that can pretty reliably identify those normal images, you can save, 10x, 100x, 1000x compute power by just running those images through the very simple classifier, rather than passing them all in to a fancy CNN and having every frame in that video processed by this fancy expensive thing that requires GPUs to run, maybe depending on how many cameras you have. We're talking about a lot of potential savings. So this is what BigML, again, what we've tried to do at BigML is giving you a platform that gives you the potential to realize this sort of speed up. If you know something about images, or if you're willing to learn something about images and the sorts of features that are good for your problem, you can train these very simple models that might, they might not be as good as a full convolutional neural network, but they're much faster. And if in the cases where that simple model isn't sure, you can pass it through to the convolutional neural network and still have all that power sitting there waiting for you. And we have a blog post about this particular case online right now. You can go. It's called the Simple and the Complex. It was the last one before the webinar, so you can go and see a more in-depth treatment of this particular scenario. So to sum up, image processing the BigML way. What does that mean? It means, first of all, that everything is immutable, traceable, and composable. So we offer you a lot of different options. We offer you ways of putting those things all together via the API. And no matter what you do, no matter how you compose the models together, what data you train on, how you feed the predictions of one model to another, all of the stuff is always, all of the stuff you build is always traceable. So you can always go back to the data that you train that model on, and you can always do auditing. You can look for mistakes. If the model is not behaving properly, you can examine the data, the training data, and see what might be wrong. This is kind of a core tenet of BigML, is this immutability and traceability. No matter how complex of a thing you build, you can always trace it back through and figure out how exactly it was built and what exactly it was built from. And then everything is available via the API and downloadable. So image dataset creation, labeling, everything that you saw me do when I was labeling the images, when I was adding sources to the composite, all of that stuff is available via the API, as is everything in the UI. Our UI is built on top of our API. And so anything that you see us doing in the UI, you could also do yourself with different graphics or different interface. You can always rebuild those interactions using our API. Models are live, as I showed, via API endpoint immediately after they're created. So productionizing a model is trivial, is already done for you after you train the model. And then also, if you have a specific case where you need to download and run the model locally, all the models are white box. They're just JSON that can be swallowed by any of our bindings, or swallowed by any third-party code that you write. If you're willing to write code to parse the models and run them, there's no reason you can't do that. You just download the models, and you again could write the same code that we wrote for our bindings. There's no special trick. It's all there, kind of in plain language. JSON is readable, and so you can always write your own code to make predictions if our bindings aren't adequate for some reason. And something I've glossed over here, okay, images are a little bit special, right? We've been treating images the whole time as simply another type of data. So you can give text data, you can give numeric data, you can give date times, and now you can give images too. But in fact, there are a few problems that are specific to images, a few kind of important machine learning settings that are very specific to images. Object detection is one of them. Maybe like the next one, if you want. After classification is you want to say, okay, there's something in the image, and this is what it is, and this is where it is in the image. So you want to draw, like, say, a bounding box around that thing. If you want to draw, if you want to classify each pixel, you've got image segmentation. So you don't just want to draw a box around the thing. You want to know exactly which pixels make up that thing in the image. That's segmentation. And then super resolution, just another example of one of these problems where you have an image at a kind of low resolution and you want to upscale it to some larger resolution. That's another machine learning problem that's kind of particular to images. And there's others. I'm just listing a few here. There's like image captioning. You know, there have been examples where people generate HTML code from an image. So all these things are kind of particular to images. And we're not doing those things right now. Our initial release doesn't support them. But as I said at the top, there's a bunch of other customers that we have using object detection in beta right now. And so object detection is very close to being made public. It's almost certainly going to be our next release at BigML in just a few months. So do keep your eyes open for that. And if you think you have a use case where you want to partner with us for object detection, give us a shout, info@bigml.com, and maybe we can work together with you as a beta customer to get something up and running.